Now let's find out what's going on when I reorder the fields of a struct. In the last lesson, I showed that when I declare the struct with these two integer fields next to one another, the size of the struct is 24. That's equal to the total number of bytes required by each of the four data types. But when I declare them in a different order, like this, so now the ints are separated by the double, now the size of the struct is 32. So what's going on? The answer is that the data types are being aligned in memory. At least this is what happens on desktop computers such as the PC that I'm using here, but it may be quite different on other architectures such as microcontrollers. To understand data alignment, imagine that I'm storing my struct in a matrix of cells, like in a spreadsheet. Now here's my int a, and it takes up 4 bytes, or 4 cells in my spreadsheet. My double B comes next, that takes 8 bytes. Another int C, another 4 bytes, and then the long int D, and that also takes 8 bytes. These data fields are arranged in memory much as I've arranged them here in the spreadsheet. They form a nice, neat, regular matrix. Now, it's not exactly the way that memory is arranged in your computer, but it might be a useful way to imagine it. The fields of the struct are aligned so that they all start at a predefined boundary. And to visualize that in a spreadsheet, I can start counting along the cells in my matrix of cells. So each 8-byte data type needs to start at some multiple of 8 bytes in memory from the start of the matrix. So I count the cells or the bytes used by A. That's 1, 2, 3, 4. But my double B can't start here in the 5th cell because that's on a 4-byte boundary. It's where the 4-byte int A ends. So I carry on counting along the 4 empty cells or unused bytes. That's 5, 6, 7, 8. And now I've arrived at an 8-byte boundary. Now the empty cells here on the right aren't used, in fact, but they are important because they help to pad out the gap between the 4-byte int and the 8-byte double, and that's how I ensure that the double starts on this 8-byte boundary. So that's where it starts there. Now, since I've used the calloc function when allocating memory, these empty cells, the ones shown on the right of the A and C ints, well, they've been initialized with nulls. They don't have to be initialized that way, but it's a good idea to do so, and it makes debugging easier because at least their values are predictable. Think of this struct as occupying a matrix of 4 by 8. 4 fields, 8 bytes wide, to accommodate the largest data type, that's the double and the long int, plus some padding, unused bytes, after the smaller int fields. Hence, my struct takes up 4 multiplied by 8. That's 32 bytes. But when I rearrange the field order by putting the 2 int fields one after the other, so that's like this, well, that changes the structure of my the layout of my structure rather to something like this. So the C compiler can now optimize the structure in memory. Instead of padding out the first int field A with extra bytes, it just puts the next data field, which is now another int, another 4-byte int, that's the C int, it puts it alongside A, and that also forms now a nice, neat matrix. But this time, no extra bytes are needed to align the 8-byte data fields at 8-byte boundaries. So the matrix now takes 8 fewer cells in my spreadsheet, or 8 fewer bytes in memory. My spreadsheet now has 3 rows and 8 columns. 3 times 8, well, that equals 24. And so now my struct takes up 24 bytes in memory. But let's go back to this version of my struct, where the int fields are not adjacent to one another. So that's shown here in the spreadsheet, where I've got the int a divided from int c by the double b, and then I've shown these nulls alongside. Let me go back into my code to put the code back into that state. So once again, I've got the ints, 2 ints, separated by this double. So let's see what happens when I run this. And there's the output of my program. So I've written this code to display the fields of the struct at index 0, the first element, and at index 3, the last element in my array. This for loop displays data stored at 4 byte offsets. That's 4 bytes because that's the size of an int, from the start of the address containing the struct at index 3. The first 4 bytes contains the int variable a, and if I look at the output, you can see that that's the value 3. The next 4 bytes is 0, that is, it contains the nulls that we used to initialize the memory when I called calloc to allocate the memory initially. The memory containing nulls is the padding. These are the unused bytes between the end of the int and the start of the double, and they are there in order to align the start of the double to an 8-byte boundary. Remember, we saw that represented in this way in the spreadsheet. So this struct contains a mix of data for the fields and unused bytes, which here are nulls, just like that matrix in my spreadsheet. Then we come to field B, which is a double. That's stored over 8 bytes. Don't worry what these two numbers are. I'm displaying a decimal representation divided up into 2 4-byte chunks of the floating point data, which occupies 8 bytes, so it's not going to make much sense. The actual numbers are not important. What's important is to note that the 8-byte double fills up 2 adjacent 4-byte chunks of memory, so no additional bytes were needed to align it. Then there's another int c. Its value is 60, that's I times 20, which I've set in my code. But that takes up only 4 bytes, so once again the 4 bytes have been added onto the end of it. This is the chunk of memory that contains the nulls that were added by calloc. And finally there's the D field, that's another 8 bytes to represent a long int. Again, the actual numbers shown here are not useful or informative, as I'm showing 2 4-byte chunks of an actual 8-byte number, but that's not important for our purposes. What's important is to see that once again no extra bytes have been added, because the full 8 bytes are used and no padding is needed to align this data field.